very simple setup and get started. The k-means algorithm. So to be precise, the k-means clustering algorithm. So you will see that when I say it is a simple setup, it's linear algebra that makes us easy for us to look at these things for actually large data sets without having to write down everything, right? So for example, I can look at, let's say, 10 samples, and we will number them as Python would do. So I would say, this is my first sample, this is my second, third, and so on, right? So these are vectors, right? So as you all know, these could be samples that may correspond to any number of features. So for example, in the glass data set, each of these is a vector of what shape, each of these for the glass data set, 9 comma empty, right? So these are your sample vectors, right? So we are not really talking about how many features you have. We are keeping it generic, right? So it could be 9 features, it could be 9,000 features, it could be 90,000 features, does not matter. The setup is still the same, right? So the first thing we have to decide in k-means, or we have to pre-decide, is the number of clusters. Of course, we'll see how to overcome this step, is the number of clusters. So I pre-decide the number of clusters. So this might look like sort of a shortcoming, but it is in some sense, but we can overcome it, pre-decide the number of clusters. So make sure you understand the k-means algorithm, the procedure, because in the exam you may have to do this for a simple setup, right? So you may have to show me how it works. I might give you a few samples with very simple looking features, and you should be able to execute the k-means in 5 minutes, right? So please practice it as we are doing it now. Okay, so pre-decide the number of clusters. So for simplicity, we'll start with 3 clusters. Let's say we start with 3. So in practice, right, when you're thinking of clustering your patients, clustering your customers, clustering the students, clustering, for example, the products that come out of a production pipeline, right? There is that optimal cluster size, right? What does that optimal cluster size mean to you? Let's take a very specific example. Let's take the example of customers, right? You want to cluster the customers, your customers, the customers who come to your store, so that you want to do what? Why do you want to cluster? It should be easy, guys. Why do you want to cluster? Let's say you run the Harsha showroom, right? Or you are helping Harsha showroom to cluster their customers. So what is it that they are achieving? Yes, Suraj? Yeah? Correct, frequent. I mean, for that you don't have to cluster, right? I mean, you can just check who is. Correct, exactly. So you get all these ideas about your customers after you have clustered them, right? So for example, you might find that it doesn't matter what the gender is, but there are customers who typically are between 20 to 30 who spend on cell phone related things, right? Or there could be one cluster where you have primarily males, right? So and they're buying something, right? So clustering is one of the steps in understanding your client base, your customer base, or in linear algebra terms, your samples, right? So you have to dive into the clusters later and then see what they speak for them. So this is what we say, that we let the data speak for itself, right? The clusters will speak for themselves. It's actually very interesting particularly from a business perspective, also from a healthcare perspective. So we had a problem where we had a fairly complex ICU data set and we clustered the patients, and we found out that these are cardiac ICUs. We found out that there were 3 clusters, 3 or 4 clusters, and typically patients from each cardiac ICU went into one of the clusters. And we did not use cardiac ICU type as one of our features, right? So it is like the data naturally speaking for itself, right? So because in the hospital, the doctors are sending the patients into one of the ICUs depending on what they understand. And here is, a validation of, what the doctors' minds are thinking. The algorithm is also doing something similar. It is saying, I will put the patients into, according to their ICUs, where we did not even use ICU as one of the features. This is quite surprising, right? The computer algorithm doesn't know we are dealing with patients. It is numbers as far as the computer is concerned. But it is sort of revealing what goes under the hood. This happens in practice a lot. So when you do unsupervised machine learning, you should always try to match your analysis with the assumptions and the gut notions of the stakeholders, right? I mean, they are the ones who know what is happening. Right? So most of the time, they will be spot on, and then you can see if the machine learning algorithm is capturing those details about the data. Okay. Now, fine. Let's say we have done the clustering, right? So let's say you have 3 clusters. Now the question is, the owner of the shop will ask you, so how did you decide that you only have 3 groups of customers? Why not 4? 3 seems to be a small number. Why not 5? Right? So there is something special about the optimal cluster size, right? That is, if we increase it further, it is not optimal. If we decrease it further, it's not optimal. So what exactly is special about that? Cluster size 3. In this case, in other cases it could be 4, it could be 5. In some cases it could even be 10 or 20, right? So there is that optimal cluster size we have to narrow down, right? And this is similar to the loss for a sample that we saw. You remember, you have a model that looks at data, and the person can be stressed or not stressed, right? You apply the model predicts something, right? And you have the notion of a loss for each sample, how unhappy you are with respect to each sample. It's the same thing here. Each sample is going to go into a cluster, right? So we are going to calculate the loss for each sample. So how unhappy we are that a sample in a particular cluster. And then we're going to average out the unhappiness, just like before. This common logic is so recurring in machine learning that as you see more and more algorithms, this should become second nature. The only thing that changes is the way we define the unhappiness, right? So how unhappy we are with, for example, a particular sample moving into a particular cluster. Okay, so yesterday we started doing this. So we said we'll have 3 clusters. So what do? So we randomly assign a sample, randomly assign a sample to each cluster and call it the cluster centroid. So that's the name we will use here. Call it the cluster centroid. So cluster centroid is like the representative, right? It is like the representative sample for that cluster. The representative sample for that particular cluster. So how could we do that here? So let's draw 3 clusters. So let's say here we have cluster 1, cluster 2, and cluster 3, right? So this is cluster 1, or I'll use the Python way of indexing, cluster 0, cluster 1, and cluster 2. Okay, so it looks like this. So let's randomly select samples. I'll pretend that I've selected X10 as, X9 as the sample that will go to cluster 0 as the representative. Let's say it's X1 here and X5 here. Now you all understand this is not a geometric diagram. It's clear, right? It's only a conceptual structure diagram. I'm saying there is a bucket where x9 goes and sits. It doesn't mean that x9 is at the center. I mean, it's structurally the center, right? Geometrically also, we'll see why. But this picture is not geometric. I'm just saying three buckets, three random samples, they go and sit. Now we call x9 as the initial centroid of cluster 0, x1 as the initial centroid of cluster 1, and x5 as the initial centroid of cluster 2. Clear? Very simple, right? So it's kind of a natural procedure. Alright, so then what do we do? What is the next step? What did we discuss yesterday? Can one of you tell me? We assign the remaining samples So what will be the remaining samples? So we have x0, we don't have x1 because x1 is already a cluster centroid. We have x2, x3, x4. We don't have x5, it is already a cluster centroid. x6, x7 and x8. To an appropriate cluster. So we will assign each sample to an appropriate cluster. Based on what? How do we decide? How do we decide which sample will go to which cluster? Based on the similarity, right? Or the distance to the centroids. Similarity is measured based on similarity, aka, or not also known as similarity, or distance to the cluster centroids. Okay, so for example, so let's say that let's consider x0. Okay, let's consider x0. So what do? We have to decide where x0 goes into, right? So what would you do? So does x0 go to cluster 1 or cluster 0, that is? So does it go here to cluster 0, or should it go to cluster 1, or should it go to cluster 2? So how do we do that? Well, we have the cluster centroid, right? So we will take the distance of x0 from the 0th cluster centroid, right? So the way I'm going to write that down, it's going to be like this. So how far is x0? What was the 0th cluster centroid? x9. So this is the difference vector. You take the L2 norm, right? That tells you the geometric distance between these two vectors, right? In practice, the L2 norm involves a square root, right? So you have to take a square root. So because what is the L2 norm of this vector? 1, 2, 3. It's the square root of 1 squared plus 2 squared plus 3 squared, right? I mean, I can take the square of the L2 norm. What will happen? That square root will vanish, right? It's no different. It's the same thing, except that you're talking about the squared difference. So you can avoid calculating square roots and things like that. So we will take the square of the L2 norm, okay? So here we'll calculate the square of the difference. And here we'll calculate how far is x0 from the first cluster centroid, square of the distance. Similarly, we'll calculate here how far is x0. Sorry, what is the first cluster? x1. This is x1. And x0 and x5 squared, right? And then what do? So we will use, we'll assign it to, so eventually we'll assign to a specific cluster. So I'll just call it cluster J. That is that has the least centroid distance with x0. That has least centroid distance with x0. So basically, you're saying in practical terms, you're just asking, who am I most similar to? That's it. So you have 3 buckets. Who am I most similar to? Just assign me to that bucket. Okay. And this you will repeat for the rest of the samples, right? So this is repeated for the rest of the samples. So this is repeated for the rest of the samples. So what is the most expensive operation here? Calculating those distances, right? But you know how to do it. And in fact, it is possible to write your code in a way such that not only it's very compact, but it will also be blazing fast. We will write it more or less like that using the class description I gave you, the object-oriented description. Okay, so we'll assume that, let's assume that this procedure results in the following initial clustering. Let's assume that this procedure results in the following initial clustering. Okay, so I'm going to say what the clusters will have. So here are the clusters. I'll just copy paste them. All right, so here are our clusters. This is cluster 2, right? So let's assume that the samples have gone and sat like this. Let's say x1 and x3 are sitting here, x4, x7 and x8, they sit here. And let's say here we have, oh sorry, I'll call it x0. It's not x1 because x1 is one of the cluster centroids. So what we have, what is left? Can you remind me? x6 is left, x2, right? x6 and x2, they sit there. Okay. This is the initial clustering. This is what I mean by the following initial clustering. Okay. So you have achieved your clustering, whether it is optimal or not, but you have achieved it, right? In some sort of, let's say, not a random way, you do not randomly throw samples into the cluster, right? But you have done it in a way that has some logic. The logic is that we assign each samples to a cluster where it will potentially belong to in terms of similarity. All right. Now, we have to decide how good our clustering is. Now we have to decide how good the clusters are. So in other words, this is equivalent to calculating a loss for each sample, equivalent to calculating unhappiness, how unhappy you are, calculating a loss for each sample. Just like what we did with the deep learning example. So you have your sample x0, right? Okay, you have your sample x0. Now, how will you calculate, or how will you quantify, and where is x0 sitting? In cluster 0. How will you quantify your unhappiness as to x0 is in a good cluster or not? It is in cluster 0. So we know that we should say whether we are happy or unhappy, right? You're thinking, fine, we just figured out that x0 will not go into cluster 1 and cluster 2, and then only we decided it will go into cluster 0, right? So we should be happy about it. So what is that unhappiness we are talking about now? The unhappiness we are talking about is within cluster 0, right? I mean, how similar is x0 to the cluster centroid? If x0 is very, very, very similar to the cluster centroid, then you're actually very happy. that it belongs to this cluster, right? So that is something we already calculated, right? So what you can do is you can say, okay, here's my x0, how different it is from the cluster centroid. This is something we actually calculated, right? But now you will use this as your loss, right? How different is x0 from its cluster centroid? So all this we are doing for cluster 0. And then what is the next sample? X3. How different is x3 from its cluster centroid in a squared sense? The square that I'm doing there is to avoid the square root, right? So that's the only reason we are doing it. And then what can you do? I can add these two, right? If I add these two, it is basically quantifying the differences. It is summing up the differences of the samples with respect to the centroid. Jayesh, you have a question? Oh, x9, thank you. Yeah. Because that is a cluster centroid, right? So in fact, what I'll do is I'll just use the color for the cluster centroid. Thank you. So x9 is the cluster centroid. Okay. So now we'll move on. So what I'll do is I'll use a slightly different color for these two clusters, right? So that we also see the clusters with respect to those colors, so it's probably easier to follow. All right, so it says it's red. And what was the cluster centroid here? X1, no? Okay. So I'll call this cluster 1. I'll use maybe green. So this is cluster 2. Can one of you remind me what was the cluster centroid? 5. Okay. All right. So now we are done with cluster 0. In other words, we have sort of quantified our unhappiness. So this is cluster 0. So now we move on to cluster 1. So let's move on to cluster 1. Okay. All right. So cluster 1. We want to calculate each sample that is sitting there. So we have x2. How far is x2 from the centroid of cluster 1? And how far is x6 from the centroid of cluster 1 in a square sense? So what is the centroid of cluster 1? x1, right? This is what we have. Okay. And finally, we move on to cluster 3. So we will be able to calculate the distances similarly. So cluster 3. Same question we ask. How far are the samples? So we have x4, x7. So x4 is the first sample, let's say. How far is x4 from the centroid of cluster 3? How far is x7 from the centroid of cluster 3? And how far is x8, which is the other sample, from the centroid of cluster 3? So what is the centroid of cluster 3? x5, right? x5, like so. All right, so now we have our unhappiness quantified for each cluster, right? So what will you eventually call as your loss, right? So we somehow want to measure a single number, not a whole lot of numbers. So how will you now quantify your loss? There is a loss for cluster 0, there is a loss for cluster 1, there is a loss for cluster 3, right? But in fact, you should think about it this way. There is a loss for the 0th sample, there is a loss for the 3rd sample, there is a loss for the 2nd, there is a loss for the 6th. In other words, we have actually calculated the loss for each sample. I've just shown you cluster-wise, right? So what did we do in the deep learning case? We just calculated the average loss, right? We'll just calculate the average loss across all the samples, because at the end of the day, what do you want to minimize? You want to be as good as possible each sample is concerned. Of course, I can take the average of this number, and this number. That will be this plus this divided by 3. When you do that, you might make sample 0 quite unhappy, and you might make sample 3 happy, so that there is a balance. But that is not what we want to do. We want to be on an average happy with respect to all the samples, right? So this is what we call as the cluster objective. So the clustering objective, which is what we want to, the clustering objective, this is also the loss, will now be the average of the losses of each sample. Okay, so how will that look like? Well, I just had all these things. I'll have to add all of them and divide by how many ever samples I have. So here it is. Okay, so here we have, so I can just add all of this. So this plus this plus this, all of this will be divided by what? 1 over the number of samples. So you're thinking, what about the loss for x9, x1 and x5? What is the loss for x9? This is the loss for the 0th sample, the loss for the 3rd sample, and so on. But we don't have 10 losses inside, the way I've written. How many losses do we have inside? There's 0, right? The losses are 0, because they are the cluster centroids. You do have x9 minus x9, because it's already the centroid, the loss is 0. Right? Does that make sense, everybody? So we calculate the clustering objective each iteration. Now we have done one iteration. What is that one iteration? We started with the samples, the 10 samples. We decided on the number of clusters, and then we randomly picked 3 samples, made them the cluster representatives or the cluster centroids, and we reassigned the rest of the samples to the appropriate cluster based on the similarity, the distance measure, right? And then we send them like so. We send each sample to a cluster where the distance to the cluster centroid is smallest. We repeat it for all the samples. We get an initial clustering, and then we calculate the loss for each sample. Finally, narrow it down to one number. So after the first iteration, you have an initial clustering, you have a loss. Now what do we do next? Obviously, this loss is the reference, right? You cannot stop here because you don't know if this is optimal or not. So what will you do? Exactly. Yeah, in a cluster, you recalculate the centroids, right? What is a centroid? It is the average of all the samples sitting in that bucket. So what will be the new centroid of cluster 0? It's simply x0 plus x9 plus x3 divided by 3. It's just a new centroid. Similarly, we recalculate the centroid for cluster 1 and so on. So let's go ahead and do that. So the next step is recalculate the cluster centroids. So how do we do that? Well, we already have the cluster assignment like this, right? So when you say recalculate the cluster centroid, what does it mean? So here we're just going to average out, right? So the new cluster is going to be the sum of, or the average. So I'll add these 3 vectors and I'll divide by what? 3, 1 over 3. Similarly, I will add these 3 vectors and I'll divide by 1 over 3. And I'll add these 4 vectors And what will I divide by? 4. Now do you see that this is one of the properties of k-means? It is highly likely that when you average out these 3 samples, you will get a new sample that is not even in your list. Is it making sense? So initially you had x9, x1 and x5. Those are actual samples that you had, right? Now when you recalculate the cluster centroids, you will get a patient, an average patient, who is not even in your list. Their heart rate, blood pressure, temperature may not be, but that is the average patient, right? So here is where k-means differs from another algorithm. There is another algorithm which is called k-medoids, right? Medoids. Now k-medoids is very similar to k-means. The only difference is in every iteration we retain one of the samples as the cluster centroids, right? So there is always a match between the centroid and one of your samples. So this is a more practically useful algorithm because when you finish the clustering, you will have a centroid who is one of your patients, who is one of your customers. So when you go talk to the owner of Harsha, you can say, oh look, this person who you have seen in your shop quite often is representative of cluster 1. So your question is, why are we not discussing that? That seems more practical. Why are we discussing this? Because the extension to this is very simple. This is the base algorithm, and you can extend this fairly easily to k-medoids and the other extensions. Distance is what makes k-means a very generic algorithm. Okay? So now you calculate the cluster centroids. What do we do next? Now you reassign all the 10 samples, right? So you repeat the process. So reassign. So you reassign now not 7 samples. Reassign all the samples, all the 10 samples. Reassign all the 10 samples to an appropriate cluster, just like how we did before, based on the distance to the cluster centroids. So you take the smallest distance to the cluster centroid and reassign the sample. And what do we do next? We recalculate the clustering objective. Recalculate the clustering objective. You guys know how to calculate the clustering objective, right? So I showed you how to do that. This is how we do it. Okay. Now in the second step, you will have losses for all the samples, most likely, right? Because x9 was the lucky fellow, just happened to be the cluster centroid randomly, so the loss is 0. But in the second iteration, x9 will also have some unhappiness associated with which cluster they are sitting in. Okay. So, and then we repeat the steps. Recalculate the clustering objective, repeat the steps. So now comes the most important question. Until what? When will you stop? Okay, Samad says that what is same as the previous? Yeah. 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 The clustering assignments, they are not changing much, right? But you know, that is what we want to do, but it's kind of difficult to do that here, like a million samples, right? So change in loss is less. The loss is what is capturing all that, right? The loss is getting smaller and smaller and smaller, but you see that after some time, there is not much change in the loss. If there is not much change in the loss, what does it mean? The clustering assignments, they are not changing much, right? We keep a threshold, and then we stop when the drop in loss kind of becomes flat. So what we do is, so until the loss decreases substantially. Now that is a subjective statement. I mean, what do you mean substantive? So what we do is we make, so this is a curve that you guys will see a lot of time. So we make a loss versus, in the deep learning terminology, we'll call it an epoch. I'll tell you why it is called an epoch, but in the clustering terminology, we'll call it iteration, right? Loss versus iteration. All right. So initially in the 0th iteration, you'll have a high loss, right? And then it will drop, and then it will drop, and then it will drop, and then it will sort of go this way, right? Now, one thing you should not do is look at the plot and decide, right? Here it might look like first 0, 1, 2, 3, 4. In the 4th iteration, things seems to have settled down, right? But that is a mistake you should not do by looking at this plot, because you just cannot see what is happening beyond that. Maybe it is still dropping down, right? So this picture is for visual purposes, but you actually have to calculate these values, the loss values, the objective values, and use a threshold. Right? So use a threshold that the loss doesn't change by, for example, more than 5%, then we stop in a relative way. Is it making sense? What I'm trying to say is, if you zoom into this picture after the 4th iteration, you might see that it's still dropping. So you should not jump to the conclusion that everything is fine at step 4, right? So you should actually numerically calculate the values. Okay, so these are the steps involved in k-means, right? So fairly simple algorithm, and it's also very easy to implement it. The only calculation is distances, and we'll see how to do that efficiently in Python. Now, all this works if the underlying features, they are continuous. So, for example, height, weight, blood pressure. Each patient is represented by height, weight, blood pressure, sugar level. Height is a continuous feature. Everybody clearly understand what a continuous feature is. Continuous means technically it can be any value, any real number between some range, right? So weight is a continuous feature. You can have 78, 78.5, 78.55, 78.555, etc. What will happen clearly in a business case, right? In a business case, you will not have just continuous features. What is one of the, let's say in the case of the showroom, the electrical and electronic showroom, what is one of the most obvious categorical feature? Gender, right? So the gender of your customer, right? The education level, maybe, right? So the income level, right? So and so on and so forth, right? You can also have categorization. Maybe according to the showroom owner, they are already categorizing the customer. The human brain does clustering in a very effective way. Maybe they have teenagers, young adults, mid-age and old age adults, right? Maybe they're doing that. So categorical variables always come into picture. So if you have categorical, let's say gender is one of the feature, will this make sense? So forget gender, let's say the income level is one of the features. Can we do this? Can I calculate the distance between samples if I know that income level is one of the features? Can I use the norm? Here, do norm. It will not be appropriate, yeah? Because income level, see, it is not only categorical, but it's also ordinal, right? So it's an ordinal variable. So we could use 4 levels: so high school, college, postgraduate, advanced degree, right? There are 4 groups. Now, somebody who is advanced is, in some sense, in terms of education, a little closer to postgraduate than they are to high school, right? So somehow this has to be captured, right? So how do you calculate distances between samples if the features are mixed type? So how to calculate distances between samples? If the features are of mixed type. So we're going to specifically look at an example. Just like the business context, we look at a very specific example. Okay, so how will you calculate distances when you have samples of mixed type? As I said, mixed type simply means that we have features that some are continuous, some are categorical, and so on and so forth. So how are we going to deal with this scenario? That's what we're going to be looking at. So here you're looking at an example where the features are age, education level, monthly income, and gender. So these are the features. So for example, suppose we wanted to calculate the distance between sample 0, so this is sample 0, sample 1, 2, and 3. So how different is sample 0 from sample 1? Now education level, I've already encoded it, right? So if I had not encoded it, so the way I have done is, like I've treated this as high school. Just reopen this. It's a photo, huh? Yeah, that's right. It's a photo, yeah. Sometimes the app also messes up, but yeah, thanks for reminding that. Okay, so we have education level 3 to 4, right? So education level, let's say this young fellow is college. Let's say this person is a postgraduate. This person is, let's say this is high school, and keep this as college. This is high school. This is college, and this is an advanced degree. Okay, so this is how it is. So the question we are asking is, how different is sample 0 from sample 1? So we're going to calculate distances. So how different are sample 0 and sample 1, for example? So how will you do this? So as you all know, if you have a categorical feature, the first thing you should do is encode, right? So we have to encode the categorical feature. So if I encode the categorical feature, let's look at education level, right? So, and we say Python is going to encode. Which level will get the label 0 among those 4? Advanced will be 0. Why? Because A first in alphabetical order. Then college will be 1, right? Then high school will be 2. Then postgraduate will be 3. Now this is clearly different to how we will think about the encoding. Now we'll give maybe high school is 0, college is 1, postgraduate is 2, and advanced is 3, right? So, but that's fine. I mean, you just have to stick to something. Gender, which gender will get the label 0? Female, right? This will be label 0, this will be label 1. Okay, so how different are sample 0 and sample 1, right? You cannot do this. We cannot calculate the difference as a Euclidean norm. What is the problem there? So we cannot calculate x0 minus x1 here. Why? What would be the problem? Yeah, as far as age is concerned, it's a continuous feature. Education level, is it continuous? No, it's not continuous, right? So which means that if you calculated the difference, right? So it would say that it's, so if I do 2 minus 3, it's minus 1, right? But that it doesn't have a meaning at all, because you don't have a vector that corresponds to, or you don't have a feature that corresponds to a continuous type, rather categorical. So we cannot calculate distances like so, right? So what would you do? So we use a different distance measure, and that is called the go with distance. So this is implemented inside Python, R, etc. Right? So it's there in R. So it's called the go with distance. GOWER, go with distance. The way it works is like this, right? So example, we are going to look at the same thing. How different is sample 0 from sample 1? So for each feature, so which is age, education level, income, and gender, we are going to calculate the distance between these feature values appropriately, right? And observe how we do it. It's actually quite interesting how this works. So here is the age, education level, income, and gender. So what's the difference between the ages? It is 19 minus 26, right? That's clear. But what we'll do is we'll calculate the difference between the ages. We'll get the absolute value, how far they are, right? And then we are going to divide it by the maximum of the age value, which is what? 19 minus 26 divided by what? There was a 45, right? 45 is the largest age, right? So it's 19 minus 26 divided by 45. That is what we call as the normalized distance between the two ages, right? So it's 19 minus 26 over 45. All right, so how about education level, right? So let's come to education level just a little later. How about income? We do the same thing. Income is also continuous, right? So it'll be 70,000 minus 95,000 divided by the max of the income, which was 1 lakh here. So this will be 70,000 minus 95,000 divided by 1 lakh. That will be the distance between the ages. Gender, very easy, right? Gender is a categorical feature, right? For categorical features, you don't say, if you do the usual norm way, it's called the Euclidean way, it's 1 minus 0, right? What if there is another gender? Let's say there are 3 genders, right? So then you'll have 0, 1, 2, okay? So 1 and 0, are they different? Clearly. Let's say there is another gender 2, 1 and 2, are they different? Yeah, they are different. But when you calculate the difference, what will you get? 1 minus 0 is 1, 2 minus 1 is 1, 2 minus 0 is 2, right? So if you have 3 genders, and the genders are 0, 1, and 2, and let's say I have a person of each type, right? There is person 1, person 2, person 3. As far as the gender is concerned, they are all different, right? But what is the distance between P1 and P3 if you do it the usual Euclidean norm way? It's 0 minus 2. It looks bigger than the difference between P1 and P2, which is 0 minus 1. But in reality, each one of them is different. There is no bigger difference between P1 and P3 than what it is between P1 and P2, right? P1 male is different from P2 female, P3 could be a transgender, for example. They are different, right? You don't have a bigger difference just because you assign the encoding 2 for a transgender, right? So what will be a more appropriate way of calculating distance for categorical variables? Use our intuition. What is the distance between these two? Either they are the same or they are different. Those are the only ways it can happen, right? So you say here the distance is 1. What about the difference between P1 and P3? They are different, so the distance is again 1. So if they are the same category, distance is 0. If they are different categories, distance is 1. Very simple, right? That is what we intuitively would use for a categorical variable. But it is not uncommon to see people load their data sets, do all sorts of things, do a PCA and use k-means, etc. on a data set that has categorical variables. Will Python complain? No, it won't complain. For as far as Python is concerned, you're giving some numbers, right? But the model will lead to absolutely ridiculous conclusions. Please avoid this very important misstep, right? This is something that is so very prevalent in the circumstances we have, and it is very common to see people dive into without even thinking how they will deal with categorical variables. I hope this example showed you clearly why calculating distances using the L2 norm will not work, right? L2 norm will show a bigger difference depending on which two different categories are you looking at. But we know that intuitively for a categorical feature, if two samples belong to the same category, the distance between them as far as that category is concerned is 0 because they belong to the same category. If they are of a different category, the distance is 1. That's it. Okay. All right. So gender, what is the distance in this case? One is male, one is female, right? The sample 0 is male, sample 1 is female. What is the distance? 1, right? 1 because categories are different. They are maximally separate. All right. Now comes the ordinal feature, right? Age is continuous. This is continuous. Income is continuous. And gender was categorical. In fact, it is special categorical. It is binary categorical, right? Because there are only 2 levels. Here we are assuming there are 2 levels, right? Education level is ordinal. Order matters, right? So how will you calculate the difference? So this person is 3 and the other person is 2, right? So you can calculate the, so it is unlike a categorical variable. Here there is a difference, right? If we treated education level as categorical, meaning order, there is no order for us. They have 4 different types. What will be the difference between these two? 1, because they are different education levels, right? If it is categorical, you will just say it's 1, because this person has 1 education level, this person has a completely different education, just like male and female. The distance will be 1, right? But on top of being different, we also have levels. There is an order. Who is 3 more closer to? What postgraduate is more closer to high school, or is it to advanced? So according to us, right, so this order is not meaningful, right? So in other words, what you would first want to do is force a particular encoding into Python, which is possible. This encoding that I have done is what Python does by default. You pass a column with these strings, it will assign 0. When you do label encoding, what will happen? It will assign 0 to advanced, 1 to college, 2 to high school, 3 to postgraduate, right? But then you will change it. There is a way to do that. I'll show you how to do it just a little later. But now we'll go ahead and change it. So how will we change it? So we'll say, okay, according to us, let's use this way of encoding. High school is 0. College is 1. Postgraduate is 2. And advanced is 3, right? So this is the more intuitive way of encoding it, right? So you are forcing a particular way to label encode. Now, how will we calculate the distance? So it looks like they are quite far because one is a high schooler, the other one is a postgraduate, right? You can do the same thing. So you do 0 minus 2, just like you do for a continuous variable, right? And then you divide by what? The maximum range, right? What is the maximum range that you have? It's 0 minus 2 divided by what? 3 minus 0, right? That is a maximum, right? So, but here it's a range. So this would be 2 over 3. So now you get the values, right? So you get the distances. So it's 19 minus 26 over 45, and here you have 2 over 3, and here you get this distance, and then the distance between their genders. So what do you do finally? So what we do finally is we take those 4 values. So this value here, this value here, this value there, and this value there, right? What do you do to those 4 values? You add them and you divide by 4. In other words, this value plus this value plus this value plus this value divided by 4. This is what we call as the distance. Oh, but this is fairly intuitive, right? What we have done is we have tackled the process of calculating distance feature type by feature type. If it's continuous, what's the logic? If it's continuous, it's simply the difference between the values divided by the maximum of that feature value. If it's categorical, very simple. Same category, difference is 0. Different categories, difference or distance is 1. If it's ordinal, again simple. We use the encoding, calculate the distance just like you would do for continuous. But what will you divide by? You will not divide by the maximum, but by the maximum range. Intuitively, let me read this out in plain English. How different in order they are in relation to the maximum possible difference between 2 samples as far as that feature is concerned. So what is the maximum possible difference? One is an advanced degree, the other one is a high school. In relation to them, how different are the education levels of these 2 samples? So it's 2 over 3, right? It's about, the distance is 60%. Okay, does that make sense? Everybody? Okay. Good. Now, this is what you will have to do when you have mixed type data, right? Don't dive into implementing k-means blindly because it will not work. Okay, so let's go into the code now. We have everything set up. So we'll open up the code. And what I want you guys to do now is the steps that I showed yesterday, which I'll run here. Okay, let's mount the drive. Okay, so the same class data set, we're going to continue. So here it is. Load the class data set. And then I want you guys to do this. Have you done it already? How many of you are yet to do it, please? Can you let me know? This step, don't feel shy. Yet to do it? Okay, please do it. So please run this cell or complete this cell. Should I zoom it further? Is it okay, guys at the back? All good, Jayesh? Swaroop, all good? Okay. Okay, so please implement these steps. And yeah, one is, as you know, splitting it into train and test. And the other one is to standardize. Okay. I'll just wait for them to complete. So we label encode and then we jump to the code, right? So I'll put it here, give a few minutes, and then we'll continue. Let's go into the k-means class. Here it is. So as you all know that at this point, this function, this special function is called the constructor. Constructor is what will run first. It is a special function that will run first when we create an object of the type k-means, right? So there are some parameters that I've given here. What is this k here? If the user does not initialize with a predetermined number of clusters, what is the number we are assuming? 3. The default value of k is 3. The default stopping tolerance is 10 to the power minus 10. That is what 1e minus 10 means. And then we also will have a default number of iterations we will run. So we'll run only 1000 iterations. And then if you go in, I'm sure all of you by this time know what this is. We say self.k. So it's like, for example, a student. What is the student's name? What is the student's roll number? So like that, if there is an object of type k means, what is the value of k, right? So this k is called, what is it called? It is an attribute of the class. Does that make sense? It's an attribute of the class. The class will own these attributes. So what should I set this equal to? K, right? Because that is what is coming in as an input argument, right? And this will be equal to TOL, and this will be equal to iter max. Now please make sure to understand the difference between k and self.k. They are different things. They might look similar, but they are different. What exactly is this little k? Little k is a parameter for the constructor method, and it has a default value 3, or the user will pass the value. So little k is a parameter for the constructor method. Self.k is an attribute that we are defining at this step for this class. There is an attribute for this class called self.k, and we will assign that attribute is equal to whatever the parameter k corresponding to the method init, the constructor method. And similarly, there is a difference between tolerance, TOL, and self.tol. TOL is a parameter of the constructor. Self.tol is an attribute of the class. Iter max is a parameter for the constructor method. Self.iter max is an attribute, right? So normally we name them like this so there is no confusion. But some people will also name them differently because, as you all know, there was a special naming convention for class attributes. What was it? Not caps. When I name an attribute, right, underscore at the end. Technically speaking, you will see class attributes named like this: self.k underscore, self.tol underscore, self.iter max underscore, right? Maybe we can do the same thing. Let's just stick to it. This is the professional way of doing it. This is how attributes are named, right? Or maybe I'll skip it because it just becomes, I'm thinking, maybe we could skip it this time. But I hope you will remember this, because when we go to the neural networks, the transformers and deep learning code will do that. The reason they do it is it's easy to identify. There is no confusion, right? Whenever you see that tail underscore, you'll know that it's an attribute of a class. You guys remember when we did the standard scalar, when we access the attributes? You remember? For example, the mean, it was mean underscore, right? So that underscore tells you it's an attribute. But we'll skip it here just for simplicity. Okay, now let's go down here. I'm just going to add a cell, and I'm going to create a k-means object, which I'll call km, right? So what you would do is typically this. You have a k-means class, right? So this k-means class will basically be used. So it's k underscore means, and you will pass all those arguments, right? So what are they for the constructor? So here we see that the arguments are k, tol, and iter max, right? So you'll just pass them in that order. So it will be k means. So for example, I can give my k as 3, tolerance as 1e minus 6, and the maximum number of iterations as 100. Now, this is how you create the object, right? So when I run this cell, it won't work now because that class definition is not complete. When I run this cell, what's going to happen is Python will see that this guy is calling k-means. It will first check if k-means is an inbuilt function in Python. It is not an inbuilt function. It will check if it is a class that he has defined, he or she has defined. And then it will find, yes, there is a class called k-means. And then it will check if there is a constructor method. Yes, there is a constructor method. What should I do now? I should use k, tol, and iter max. But what are the values that I should use? The values that the user passes here. K will be 3. Tolerance will be 10 to the minus 6, and iter max will be 100. And those values will be used to set the attributes. I hope it's clear to everybody that this step in object-oriented terminology, what is this called? This step. Yeah, yes. Swaraj, a little louder. Object creation or object instantiation, right? You are instantiating, you can call create, right? But we say instantiating. You are instantiating an object of what type? K-means, right? When you instantiate an object, the first thing that will happen is the constructor method will run. So it will run the init method. And inside the init method, what do? We set the attributes. So after this step, when you execute this cell, this object, little km, will have 3 attributes associated. What are they? km.eol, km.little k, and km.itermax. What will be those 3 values? The values that you pass here, right? That is what the instantiation step is. Make sense, everyone? Clear? So as you move, this should become second nature. Okay, so just to demonstrate that, let's go up. All right, we have defined the constructor, and now we'll go into a function called fit, right? Now, whenever, to be precise, this is a function inside the class, so it's called a method. It is a method that belongs to the class k-means. What is this method doing? Well, what does that self mean? This means we are writing a method for this class. Any object that we instantiated can access this method, right? So that is why we give a set. It is possible to define a function inside a class. It will not be a method. It won't be. It won't have the keyword set. This means an object that belongs to the type k-means can access this function through its name, and that is what we refer to as self, right? And what is the other parameter? The other parameter is the actual data that you are trying to cluster. So that is what I have passed as data. Okay? So now comes the fun part. So this function is called fit, right? So technically speaking, I should have called this as fit and transform because I think I'm also transforming the data. Yeah. Yeah, technically speaking, what does fit functions do? They calculate the parameters required for that process. If it's standard scaling, calculates the mean and the standard deviation. If it's label encoding, what should be the names, right? It is not actually transforming it. But if you see here where we will transform it, but we'll change the name later. For now, we'll leave it as fit. Okay, so something's happening inside this. What is it that we are doing? Let's go to the first step. And I think it's clear what we are doing here, right? So we are creating an empty dictionary to store the cluster representatives, right? So the idea here is we are going to have a dictionary that looks like this. So this will be a dictionary, and this dictionary will have, for example, 0 as one of the key, right? And what are the samples that sit there? x0, x3, etc. And it will have 1 as the key, meaning cluster 1. What are the samples that sits there? At this point, we don't know this dictionary, right? So we're going to create an empty dictionary that follows this structure. So how are we going to do this? There are quite a few ways you can create empty dictionaries in Python, but we'll just use the straightforward way of doing it. So let's go to the code. What is the easiest way to create an empty dictionary? Self.centroids is equal to this. That's it. Please go ahead and do that. We create an empty dictionary. And then what is this function here? So we're going to use, well, why is it saying random is not defined? Did I not define it above? Yeah, I haven't defined it. That's weird. Yeah, let's go ahead and define random. So add import random and run it. All right, so let's give me 1 sec. So I'll show you some examples here, and you can use that to start filling in this code here. So we are now at this step where we have created an empty dictionary. What we want to do is we want to randomly select samples and assign them as the cluster centroids. So let's go ahead and see how we can do that. So this is going to involve things that you have seen already. So this is going to involve, for example, dictionary comprehension and list comprehension, things like that. So I'll show you these examples here. Okay, have a look at this. So what is happening here? So let me load the data into X to start with. So I'll use this as the reference. Give me 1 sec. Okay, this is the same code, but I've split it into smaller pieces, so which I'll show you, and I want you guys to execute them alongside. Okay, so now I have. Alrighty. So, what is inside X? X is our data matrix, right? So I have the aluminum and refractive index and aluminum percentage inside. So what will be the shape of X? Why this is slow? Yeah, here it is, right? So you have the refractive indices and the aluminum values. So what will be the shape? So how many ever samples you have, comma, the number of columns, which is equal to 2. Yeah, 214 samples and 2 columns. Everybody clear what X is? Okay. What will I get as the output of this function? What is length of X? 214. When I say range of length of X, what happens? I get a range object from 0 through 230, right? There is also an np.a range. What is the difference between range and np.a range? Well, np.a range will actually create the values 0, 1, 2, 3, all the way till 230, right? Sometimes you may want to create the values. Sometimes you just want to say, I have a range of values. I have a range of values from 0 to 213. You don't want to explicitly create them, but it's what is known as an iterable in Python. So I hope you guys are aware of this term, right? You can iterate over that object. It is a range object. Now, what is this random.sample function? This random.sample function is going to look at a list of objects, the blue highlighted part, and is going to select 3 from them. So what is the list of objects we are looking at? 0, 1, 2, 3, all the way till 213. From that, we are selecting 3. So if I run this, I should get 3 indices randomly. So these are the 3 samples that will be the cluster centroids, the 3 cluster centroids, right? So if I run it again, I'll get 3 different. Oh, here I've set the random seed. I don't know why the negative number works. There was some complaint yesterday, right? That negative seed doesn't work. Anyway, so yeah. So you will get the same because I've set the random seed, right? So if I remove the random seed, you will get different values. But this is what we're going to do here. Did you all look at it? Clear? Please go ahead, type it up here. So we are first going to select here random indices. What is this first question mark? Where are you selecting from? It's the range, right? So it's a range of what? 0, comma, length, or you can just say length of data, but I'm just making it explicit. You can just say length of data, that is also fine, right? So it starts from 0 and we are just making it explicit here. Okay, and what should I put here? You put self.k, right? So now we are going to start making use of the attributes of the class. You want to select self.k random indices. Is it clear? Just like what we did there. The self.k is what I hard coded as 3 here. But here it is an attribute of the class, so I'm typing self.k. Please go ahead, type this up. Okay. Everybody done with this? Okay, let's go to the next step. How do I extract the rows corresponding to sample 34, 145 and 205? We know X is a NumPy array. I can use this as my row indices, right? What is that? That is precisely 34, 145, 205. If I run this, what will happen? I will get the value corresponding to sample 34, the value corresponding to sample 145, and the value corresponding to sample 205. You see that? Those are the samples. Is it clear, guys? Now, we are going to create a dictionary like so. So look at this example. What is this dictionary? This dictionary has 2 keys, centroid 1 and centroid 2. What are the values? Well, this is the value for the 0th key. This is the value for the first key, right? Now, is a dictionary a mutable or an immutable object? Mutable? It is. So we can modify the keys, right? So clearly that is the whole point of a dictionary. So I can go to my dict, and change. So before it was this. So I'm focusing on my dicto 0, which will not work, right? So in OR it works, in Python it will not work. It will complain that there is a key error here. That was the point. So let's just comment it and write again. So you can change a dictionary, you can mutate it. So the element initially that corresponded to centroid 1 key was 1 and 2. And now we have changed it to 10 and 20, right? So it is a mutable object. Okay. All right. Let's go to let's go to this step. We are going to initialize the centroids using k random elements sample from the data set. How are we going to do that? We are going to use dictionary comprehension, meaning we are going to create a dictionary. So just go ahead, create that pair of square brackets. So what do we want the key for the dictionary to be? Remember, what is this dictionary? It has the cluster information. 0th cluster, what is a centroid? That is a key. What are the values? The samples that correspond to that cluster are the values. Is it making sense? The second key will be, whatever samples index that corresponds to the centroid of that cluster, second cluster, and so on and so forth. So here, I'm going to do this, I colon data of j. So at this point, it's not clear what that I and j are, right? But I'm sure you can see what data of j would be if I give j as a specific value. That data that you see there and the x that you see here, they are similar. Have a look at this. If I print x, that's the same as the data that you see. X is what? The refractive index, and so I can, for example, go ahead, access x of 34. This will give me the 34th row or the values corresponding to the sample with index 34, right? So this is the same as data square brackets j in that code, other code that I'm showing you, okay? All right, now this is what we want to do eventually. Have a look at this. Have a look at this line here. This one here. What do we have there? I mean, I have, just for simplicity, I put 1 here. In cluster 1, what are the samples? What do I have? I have a list of samples, right? In cluster 2, what are the samples? I have a list of samples. This is what we want to do. At this point, we don't yet have the samples randomly assigned. At this point, all we have is the centroid that we have randomly selected. So we want to create this dictionary now. This is what we are doing there. So let's go there and create this dictionary. And how do I do that? Yeah.
Practically, 2 can't be in cluster 1.
This is just a random example, not pertaining to the data. Yeah.
Practically, it can't be.
Practically means I'm not getting it.
Like we are the keys plus centroid. The key A.
Oh, you're saying the key cannot be 2, right? So, but that's what we're going to do. So the key will correspond to the cluster number, right? So cluster 1, cluster 2. The key is the cluster number. Is it clear, guys? Okay. And the values will be the list of samples that sit inside the cluster. So how are we going to achieve this? So we're going to achieve it this way. Have a look at this. I've set k is equal to 3, right? What am I doing here? Random indices. This step is clear to everybody. We are randomly pulling out 3 indices from 0 to 213. 0 through 213. What is that zip here? Now, let's split it into 2 parts. I am zipping 2 things. The first thing that I'm trying to zip is range of k. What is range of k? K is 3. Range of k is 0, 1, 2. So I'm zipping 0, 1, 2, which is an object, with random indices. What were the random indices? It was also an object with 3 elements. 34, 135, 200, something like that. So there are 3 values here. There are 3 values here. I'm going to zip them pair by pair. Is it clear, everybody? 3 values in range of k, 3 values in random indices. Okay. And then each time I zip them pair by pair, I'm going to copy a value from 0, 1, 2 range of k to I. I'm going to copy a value from here, from the random indices to j. And then I'm printing I, printing x of j. In other words, what's going to come out of this? It's going to show me this. First time, the value of I is 0, and then the value of j is 34. So I is 0, and x of 34 is the 34th sample. The next time, the value of I is 1, the value of j is some 135 or something. So you have 1 and x of 35. The next time, the value of I is 2, the value of j is the last random index. I get I and x of j, the sample corresponding to the last random index, right? So, is this clear? This is our initial, this is how we want to create the initial clustering, dictionary. You have the dictionary keys, which are 0, 1, and 2. So the keys will be the cluster number, 0, 1, 2. The values will be the list of samples that will sit inside a specific cluster. To start with, we just have the random samples. So this is what we're going to implement. So let's go to the other code. Now is it clear what that I and j should be? So here we say for I comma j in what? So this is what is known as dictionary comprehension. Instead of writing the for loop line by line, you write it in one shot. I am creating a dictionary. So here, before you type this, you are saying Python that I'm creating a dictionary whose key is I and whose value is date of j. So Python will ask you what are I and j. Now you tell Python that okay, I and j, they're going to come from a for loop like so. So what are we going to zip here? What is the first thing? Range of k, range of self.k. That will be from 0, 1 to 2, right? And what is the other thing that you zip? Random indices. Okay. So, do you all see that when I run this step, right, I get what the centroids are. So, like here, my 0th centroid is what? Or the 0th cluster centroid? This sample. What is my first cluster centroid? This sample. What is my second cluster centroid? This sample, right? So what I'm going to do is, let me just replicate the same thing here with the dictionary comprehension. So instead of writing this for loop like this, I can create a dictionary using comprehension like so. Can you guys see that this is what we did? And I can remove this. Is it clear, folks? This is the same thing. Instead of x, we had data, right? Now I can run this. You construct the dictionary in one shot using that comprehension, right? There you go. Now we have created our centroids. It's a dictionary that has the 0th centroid, the first centroid, the second centroid. What is the 0th centroid? This sample. What is the first centroid? This sample. What is the second centroid? This sample. Is it clear, folks? This is what we did there. Okay. All right, so let's move on to the next step. Okay, so now we're going to begin the k-means iteration. We want to set the clustering objective. The clustering objective is also the clustering loss that I showed you, right? So what's the clustering loss? This thing here. This one here. This is the clustering loss. that single number. We want to set that equal to 0, right? So the question mark on the right hand side should be easy to fill. What should be that? 0, right? Now here we have to create a variable, right? Now we have two choices. We can either make it just a variable, give it a name that's meaningful to read, or make it a special variable which is an attribute. So would you prefer this, or would you prefer that it becomes an attribute of the class? An attribute, right? Because see, at the end, clustering objective should belong to the object, right? I mean, it's an attribute that we should be able to recall, right? So it's probably better to give it a name that's meaningful and make it an attribute of the class. So self.clustering objective is equal to 0. Okay, what do we do next? We run over the maximum number of iterations, right? So what should be this question mark? Self.itermax. Self.itermax. And now we will create an empty dictionary to store the samples in each group or cluster, right? So again, I can give it a variable name that is meaningful to read, but I'll make it an attribute, self.clusters. So what are we doing here? In the previous dictionary that we created had the centroids. The dictionary that we are going to create now will also have 0, 1, 2 as the key. But what will be the values? The values will be the list of all the samples that sit in each cluster, right? So it will not just be the centroid sample, it will be a list of samples that look like this. So it's very similar. So how do we create that dictionary? So you can actually do it the same way. So all we have to do is say that at this point there is nothing in each sample, right, or in each cluster. So what should be this question mark? Self.k. Good. Now why is it self.k? What you're basically doing here is you're saying, look, I'm running over range of self.k. What is self.k? 3. So I will be 0, 1, 2, right? For the first time, self.cluster, what is it? It's a dictionary. I is 0. What are the elements sitting in the 0th cluster? Nothing. We don't know yet who is sitting there. What are the elements sitting in the first cluster? We don't know who is sitting there. What are the elements sitting in the second cluster? Empty, right? In other words, we are just initializing the clusters 0, 1, and 2. And now we will fill it in later, okay? So, what we are doing is similar to this step here. Let me just copy paste it here. We are creating an empty dictionary, and then we initialize each cluster like so. And then I can print my clusters here. Looks like this. Okay. What kind of a data structure is clusters? Dictionary. This I here, what are we doing here? We are accessing the dictionary using the key, right? Or in other words, we are actually specifying what the key is. At this point, we haven't even specified what the key is, right? But when you do this, you're telling Python that I'm going to use the value of I, 0, 1, 2 as the key. And what are the corresponding values? Right now it's empty. Now we'll add more and more samples, right? So there are two dictionaries that you guys have now. There is a dictionary for the centroid, this one on top, and there is a dictionary for the actual clusters, right? So obviously the centroid for each sample should go and sit here, right? but then we'll do that as a separate step. We're not doing it together. We're just initializing these lists as empty, and now we'll push the samples in there. Let's go ahead and do that. This is what we're going to do next. Okay, what is the next step? The next step, let's go on this way. So this is the next step. As you all recall, we want to find the distance of a data point and each one of the K clusters and choose the nearest centroid, right? What are we doing now? We have our 214 samples. We want to know which cluster it will go to. So you run over all the samples, right? For sample in data. What is inside data? Well, all your samples, okay? For sample in data, we want to calculate the distance of the sample to each centroid. This is an interesting step. How would you do it? So how do you calculate the distance of the sample to each centroid? Let me show you here. So in our case, it's for sample in X, right? So that means you're running over all the samples. So I can just call data as X. So it's the same. Data is equal to X. Run over all the samples, right? At this point, remember, we do have this cluster called the centroid. Oh, I'll just call it centroids. Let me give it a name. Centroids is equal to that. Okay, so we have the centroids, the dictionary called the centroids. So you're going to make use of the powerful features of NumPy to make this code run faster. Of course, you can do all this using for loops. It's not difficult. I mean, the only for loop we'll use is running over the data. That is the only for loop that you will see in the code. Everything else is done in a vectorized fashion. I don't know why this thing takes so much time. Anyway, let me just type the code here. For sample in data, we want to get the distance of each sample to each centroid and then get the minimum of that, right? So there is three centroids. We want to get the distances. So first of all, how do I get the sample? Here's a sample. And I want to know how far it is from self.centroids, right? So can I do this? We'll just see if it will work. So here are my centroids. So these are the centroids. So let's just try if this works. Self.centroids for sample in data. How different are the samples from each one of the centroids? So Python will complain. One reason is sample is a NumPy array of what size? 214,3, right? Self.centroids is a dictionary with 3 elements. You have 3 dictionaries. Of course, you would love for this line, this code line, to calculate the difference of each sample from each one of the 3 centroids and present it to you, right? I think one day it will happen, right? So right now Python doesn't work that way because the broadcasting rules are kind of complex. So you will have to make sure that you present this information in a way that's applicable to Python's broadcasting rules. Okay? So is it clear? This is 214,3 sample. How many elements do you have in centroid? You have 3 elements. So Python really doesn't know how to subtract these 2 things. But we know that take the sample, get its difference from each one of the elements here, and then find the minimum of that. So let's go ahead and see how we can do this. So it will give an error message. Okay, obviously there is no self. Okay. This thing is slow for some reason. Okay, so unsupported type. It's saying, oh, this is a dictionary. See, I cannot subtract a dictionary from a NumPy object, right? So it's complaining. So what we can do is this, at least. So we can help Python a bit. Okay, why don't you calculate the distance from each centroid, and now I will run over each Python will ask what is that centroid. For centroid in self.centroids. Oh, there's no self, there's the other code, yeah. For each centroid element in the centroids dictionary, here it is, right? You go to each element and you get me the difference. So for centroid in centroids, if I get the centroids of centroid, this looks a little weird. What are we actually doing if I printed this? For centroid in centroids. So each time centroid is taking the key here, 0. First time centroid is 0. Second time centroid is 1. Third time centroid is 2. When you run a loop over a dictionary, the key values are copied to the loop variable. Centroid is 0, 1, 2, right? So, and then we are pulling out centroids of 0, is this. Next time centroids of 1 will be this. Next time centroids of 2. So we're basically pulling out each centroid element. So that's what happens here. And that's what we're going to, and that's what we did here. Okay, so of course here we want to create a list of differences. So we'll make it a list comprehension, right? Now what is this list? This list is how far is a sample from each one of the 3 centroids. But then remember, in calculating the distance, we didn't just calculate the difference vector. We did something after that, which is the norm. Which means I have to get the difference and take the norm of that. Right? So get the difference and the norm of that. So which means here, so now you see, I have the centroids. So we'll say np. How do you get the norm in Python? np.linalg.norm. By default, it will calculate the L2 norm, right? And yeah, so you calculate np.linalg norm of this for centroid and centroids, right? And then what do you want to do? You want to get the minimum, right? So the minimum of this, that we'll see later. Okay, so if I run this now, hopefully it will run fast. So what should we see as output? We have to see 214 rows coming out, and each output will be a list of how many elements? 3 elements, right? Because we are calculating how far each sample is from centroid 0, centroid 1, centroid 2. So there will be 3 values coming out here for all the 214 samples. Okay. Is there still a message? Oh, I'm not printing anything here. So yeah, I'll just call it as sample distances to centroids. This is what we are calling it there. Okay, this thing is just slow here. Let's just wait. Okay, so anyway, let's go ahead, type it here. That's what we are doing here. So it's going to be a list. What is inside? We had how different each sample is from the centroid, right? So you had self dot centroids of centroid, but then centroid is a loop variable, right? So for centroid, in self dot centroids. I hope it's clear to everybody. When you run a for loop over a dictionary, it will run over the keys of the dictionary. It's clear, right, everyone? I hope it's clear. Let's see if this is run. This is just horrible. Anyway, so let's try. And then of course we add the norm. You have np.linalg.norm of this, which means you're basically calculating how far each sample is from the centroid, from each one of the 3 centroids, for all the centroids. Okay, this is connected. Please go ahead, type this up. This is what we're doing. Okay, so now it's done. So let's see what's inside sample distances to centroids. All right, this virtual machine is particularly slow. Anyway, so now we have to get the nearest centroid index for each sample. That's weird. Yeah, it's just printing the last one. That's okay. Yeah, this is for the last sample, of course, right? So, but what I have to do is, I have to get the sample distances, which I am getting it here, and I want to get the nearest. So in other words, I have 3 values, right? What is the smallest of these 3 values? Clearly this guy, but I want to get the index of the smallest value in a list. How can you do that? How do you get the index of the smallest value? The answer is 2. In other words, this sample has to go to which cluster? Cluster 2, right?
So use minimum function and pass it to index function.
Correct. Yeah, you can use minimum, right? So what you want to do is you do have this and you want to index. Remember, what kind of an object is this thing? What kind of an object is this? It's a list, right? So there is, you can convert this list into, there are 2 ways of dealing with this, right? So you can convert this list into a NumPy array. You can convert it into a NumPy array. And once you have a NumPy array, you have some powerful functions. So for example, there's a function called argmin that will give you the index of the smallest value in the NumPy array, right? So for example, I can say np.argmin of this. Man, this machine is just screwed up. So this is also fine. You can do this. I can get the index 2. The other way of doing it is to treat it as a list, right? So I think this code is a little inefficient in that I created the values as lists, but I could have created the values as empty NumPy arrays. Now this code would have become more efficient, right? So, but just for clarity, I created as a list. So instead of creating as an empty list here, you can just say np.array and you can just say it's empty. This is also fine. This would make the code more efficient. But let's just treat it as a list because we can get to play with. So now it gives me 2. This is much easier, right? So you can change the code if you want to, but if you want to treat it as a list itself, what you don't have an argmin. So this function argmin. So it works for numpy arrays because it knows that the numpy array has elements of the same type. Now a list is a heterogeneous data structure, right? So it can potentially, it works because it has the same type of elements, but potentially it can have different types of elements, right? So Python will complain if it has different types of elements. You can do this also, this is also fine. So here we can say np.argmin sample distances to centroids. Getting it? For each sample, we are getting the nearest centroid index. By the way, this code was not generated with ChatGPT, right? So even though it reads like that. Okay, what do you want to do now? Now, this is one of the reasons why we had this as a list. You can do it as a numpy array also. What we want to do, now we have identified that this sample has to go to cluster 2. What do we want to do then? We have this dictionary called clusters. We want to append to which key? The key that we found here, which value? The sample that we have been looking at, right? So how do you append to a list? First of all, to what list are you appending it to? So you are in self.cluster, and which element you are looking at? Nearest centroid index. For example, it's 2. So right now the list is empty. Where did I create it? Yeah, it's not here. Okay, right now the list is empty. Self.cluster of nearest centroid index, right? I created this somewhere on top, isn't it? Yeah, here it is. Right now it's empty, right? So I want to go and append to this list. Is it making sense, everyone? Here is the clustering list. I want to go to this key, and I have the value, which is the list of samples that belong to this key. I want to append to this list. So first of all, I have to access self.clusters of 2. What is that 2? That's the nearest index. After accessing it, I'm getting the value, which is a list, to which I have to append the sample. Right? That's what we're going to do. Let's go ahead, append the sample. So we have accessed self.nearest index. What kind of data structure is that? A list. Excellent. And how do you append to a list in Python? Dot append. And what do you want to append? The sample. Self.clusters. Thank you. And now we are going to recalculate the cluster sensor. This for loop, right? So you see it's over. What is this for loop doing? It's taking each sample and it's putting it into each one of the 3 clusters, right? This for loop is done. What do we do next? We recalculate the cluster centroids, right? Okay, so how do we recalculate the cluster centroids? We have to run over each cluster and we have to reassign the centroid for each cluster as what? The average, right? The mean, right? So the mean of the elements sitting inside the cluster. So I can go ahead do this self.clusters of cluster. What will I get if I do this? Try to understand there are 2 dictionaries here, right? That's all I want you to keep track of. Self.clusters, what is that dictionary? It's the dictionary of the clusters themselves, right? The keys are 0, 1, 2. What are the values? The list of samples sitting in each one of the clusters. self.centroids, that is also a dictionary. The keys are again 0, 1, 2, but what are the values? That one sample or whatever that sample that corresponds to a centroid is. So that is what we are reassigning. The centroid of the zeroth cluster will be the average of all the samples sitting in the zeroth cluster. The centroid of the first cluster will be the average of all the samples sitting in the first cluster and so on. This object, what I have highlighted there, is a list. It's a list of all those samples right now sitting in the zeroth cluster. How do I get the average of them? Mean. You just have to apply the mean function. But interestingly, remember this is a list of lists. So let me just create a list of lists to show you how things can happen differently in Python. And then I think I'll stop for now. Let's go here, add a code. So here is a list of lists. So let's say it's 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I'll print it. So can I, if I do this, mean, right? So list of lists. So there is no mean, sorry, I wanted to type np.mean. np.mean. So Python knows that, you have a list, and NumPy functions will work if Python knows that all the elements in the list are of the same type. At this point, Python knows. That's why that argmin also worked. Okay. So when I said np.mean, it gives me the number 5. So what's happening? What is NumPy doing? Mean of all the numbers. It just said add all of them and divide by 9. But we wanted the mean of this plus this, right? So in other words, we wanted to calculate the mean slightly differently. If this is a NumPy array, what is the shape? So in fact, I'll add one more just so that the numbers are not the same. So let me add one more element. 10, 11, 12. So if this is a NumPy array, what is the shape? It's a 3 object that is repeating how many times? 4 times. 4 cross 3, right? So it's a 4 cross 3 NumPy array, and each row represents a sample, right? 1, 2, 3 is that sample, first sample. 4, 5, 6 is the second sample, and so on. And we wanted to calculate the mean along which direction? 0. Axis equals 0 direction, right? So if I said np.mean, so first of all, let me just turn it into a NumPy array so that you see how it looks like. np.array of lists. And if I said comma axis equal to 0, is it clear how it's showing up? A 3 object repeating 4 times. If I said axis equals 0, that means we are applying the mean operation along this direction. 1 plus 4 plus 7 plus 10 divided by 4. 2 plus 5 plus 8 plus 11 divided by 4. 3 plus 6 plus 9 plus 12 divided. So this is the average, right? The average of these 4 samples is this guy. So now you know what to do there. Right? Let's go ahead, fill it up, and then we'll stop. So we go here, we say it's the np.mean of self.cluster, clusters of cluster, comma, axis equal to 0, just what we typed. Okay. Now, the next part, I'm sure you guys should be able to complete at this point. It's not a big deal. So here we are just calculating the clustering objective. The same thing I talked about, right? So it's quite easy. So think about how you would calculate the clustering objective. I'm doing it not sample by sample, cluster by cluster. In other words, I'm going to each cluster, I'm calculating the loss for each sample and adding it, finally dividing it by the number of samples. So this is the same step that we are doing here. So first I calculate this for the zeroth cluster, this summation, and then I'm adding them all together, divide by 10. That's the same thing we're doing here. I'm sure you guys can try doing this. It's not difficult, right? And yeah, and then here we're just printing the iteration details, and here we are breaking out. See, of course, you don't want to go through all your 1000 iterations. You should break out of the loop if your clustering objective is not changing in a relative sense too much, right? There is the old clustering objective, which is what we call a self-taught clustering objective. There is a new clustering objective. So what should be this question mark? The new clustering objective. So what is the difference between the new clustering objective and the old clustering objective in a relative sense, not the absolute sense? So is it clear? In a relative sense. The reason why you have the relative sense is, are these two numbers very different? 4.01, 4.001. In an absolute sense, they are not very different, right? When you get the difference between these two numbers, it's very small in an absolute sense. But in a relative sense, they are actually very different. How good is 4.01 as an approximation to 4.001? It is actually bad. When you calculate the difference like this, right, you're going to get 0.009. Right, this is what you're going to get, right? In an absolute sense, the error is small, but when you divide by the relative sense, you will see that it's a big number. And this is what we are calculating. New objective, old objective, new objective in a relative sense. If it is bigger than, if it's smaller than the tolerance, which is self-tall, right? You break. Break from where? Where do you break from? Whatever the outermost loop you are writing, right? So what is the outermost loop you are writing? Don't lose track of that. It was for the iterations, right? This one. You will just break out of the loop. You won't continue further, okay? And that's it. So I'm sure you guys can do that. In fact, you can get to this point. You can actually comment of all these, right? This is the prediction one. It's not very difficult. It's along the same lines. But you can certainly get to this point. Please try this. Okay, I'll stop here. So we'll start APS at 11:05. So you have a 15-minute break.